what about the boundary of a manifold with boundary? All the interior points form a manifold without boundary themselves. And is boundary an object in its own right? Well, if I'm a one-dimensional manifold, my endpoints are points. Okay, so these are zero-dimensional manifolds without a boundary. Okay. If I consider a two-dimensional manifold, so a surface, and it has a boundary, then that boundary is a path along the wall. Well, there are several components, several passes, but so again, this is circles, one-dimensional manifolds without boundary, one-dimensional, three-dimensional manifolds. Their surfaces, their boundaries should be surfaces. So we would expect that the boundary is again a manifold, but one dimension down, and does not have a boundary itself. And that's exactly the next proposition. If M is a k-dimensional manifold with boundary del M, then the boundary of a manifold is a k-1 dimensional manifold without boundary. So like here, my two-dimensional manifold with boundary, so that would be a one-dimensional one without boundary. And how to prove that? Well, to show that I have a manifold without boundary, I should write parameterizations from R k-1 into the manifold. So I want this to be inherited from the parameterizations of M. So as long as I can restrict everything just to, so here's my upper half space, as long as I can restrict everything just to the boundary part, then I have a k-1 space mapped into my boundary, and this is what I need, right? So this is exactly how the proof works. So show that if the boundary point is in the boundary for one local coordinate system, then it's also in the boundary for all other local coordinate systems, and we can restrict. So if x is in the boundary point, then we do have a local parameterization from u to v, where u is an open set contained in HK, because we have a manifold with boundary we start with of k's dimension, and we go into M as the open set in M. So then we have to show that indeed this image of a parameterization of the boundary of the manifold is then going into the boundary of the set in the manifold. Then we can do exactly this argument, because we keep the boundary on the boundary. So then we have a parameterization here of R k-1 with subspace. So how do we do that? That we do by a contradiction. We assume that there's one parameterization where the point is kept in the boundary and another one where it's not. And then we show that's not going to work by the inverse function theorem, because if a point is in the interior, there's an open neighborhood, and then if both were parameterizations we have bijections and other first derivatives, so there should also be an open neighborhood in the space around the other point, and that's a contradiction to the one of the points having been on the boundary. So I'm just writing down what I just said. So by contradiction, if x is not in the boundary for phi, but there's another parameterization psi for which it is in the boundary, so that goes from W to V, same V, different patch in HK. But so here x is in boundary with respect to that. So then if we combine the two, first psi and then phi inverse, that maps a boundary point to the interior point. Maps boundary point to interior point. And that gives, by the inverse function theorem, realizing that it is a differential in the first derivative. The first derivative is bijective, so we can use inverse function theorem, and we get G inverse maps and, well, this is then an open neighborhood of x in R K, and that's a contradiction to x having been a point in the boundary of W. So one remark maybe, namely, so here's again our manifold with a boundary. So the tangent space of this k minus 1 dimensional manifold, that would be now you can really forget about the original manifold around it, so that's just this line, and that is a linear subspace of the tangent space of the manifold at this point, the bigger manifold, and it has always one dimension less. So this one is, if this is x and this is m, so then this is the tangent space of x with considering with respect to, so considering this this boundary manifold, and the two-dimensional thing would be the tangent space from last video, and this is a one-dimensionless, so codimension 1 linear subspace of this. Works in all dimensions because, well, we're only using one dimension by going from the manifold to its boundary.